right, let's talk about something that every engineer, every scientist deals with. You take a measurement, you look at the number, and you ask yourself, can I really trust this? Well, in this explainer, we're going to dig into exactly that. We're talking about measurement uncertainty. We're going to pull back the curtain, show you how to spot those sneaky, hidden errors that can mess up your results. And even better, we'll show you how to fight back. Because when it comes down to it, accuracy is king. Okay, so here's how we're going to tackle this. First, we'll look at systematic errors, then how to fight them. We'll do the same for random errors. After that, we'll dive into this invisible threat called induced noise and how to design for clean signals. And finally, we'll wrap it all up with a master plan. Let's jump in. All right, section 1, systematic errors. Let's call these guys the consistent culprits. Think of this as the error that just won't quit. It shows up every single time, predictable as the sunrise, and it's always pushing your data in one specific direction. It's that nagging little bias that can drive you absolutely crazy. So the big thing to remember here is that these errors are not random at all. They're happening for a reason, right? There's some kind of flaw in your setup, and until you find it and fix it, that error is going to keep showing up. You know that bathroom scale that always reads 5 pounds heavy? Yeah. That's a perfect classic example of a systematic error. Okay, so where do these sneaky errors actually come from? Well, they tend to hide in 4 main places. First, the act of measuring itself can be the problem. Then you've got your environment messing with things. Of course, there's good old wear and tear on your gear. And believe it or not, even the wires you're using can be a source. Let's break each one down. This one's a bit of a mind bender, right? It's like the classic observer effect. Just by trying to measure something, you actually change it. That example of the cold thermometer in hot water, it's perfect. You stick it in, thinking you're just getting a reading. But what you're really doing is also cooling the water down just a tiny bit. The measurement itself is interfering with the result. Wild. And then there's the world around you. Your lab, your workshop, wherever you are. It's not a static bubble. The temperature goes up and down, the humidity changes, maybe even the air pressure shifts. And all of that can subtly, or not so subtly, trick your instruments. It leaves you wondering, is that a real change I'm seeing, or is the room just having a moment? Okay, and here's where it gets interesting. These environmental effects can show up in 2 different ways. The first one is called zero drift. This is where everything just shifts. Your 0 point is no longer 0, and every single measurement is off by that same amount. But then there's sensitivity drift. This one is a little trickier. Your 0 might be perfectly fine, but the scale of your measurement gets warped. So a small reading might be accurate, but the bigger the value you're measuring, the bigger the error gets. Okay, section 2. We know what these errors are. Now how do we get rid of them? Let's dive into the toolkit for accuracy. So here's your 6-step battle plan. It really starts with smart design, like using materials that don't change much with temperature. Then you've got to do regular calibration. That's just non-negotiable for correcting drift. You can also get clever and use opposing inputs, where one component cancels out the error of another. High-gain feedback is another powerful tool. It makes your system rely on a stable part, not the flaky one. Of course, filtering out no noise is huge. And finally, the really cool stuff, using intelligent instruments that can literally sense what's going on and correct themselves on the fly. But let's be real for a second. Sometimes you just can't get rid of an error completely. It's just there. So what's the next best thing? You have to quantify it. You have to be able to say, okay, I know my measurement isn't perfect, but I know how imperfect it is. Putting a number on that uncertainty is absolutely crucial. One way to do that is the worst case scenario. You basically just find every single possible source of error, assume they're all at their absolute maximum, and add them all together. It's conservative for sure. You get a number that you know the error won't exceed. But honestly, it usually overestimates the problem by a lot. A much more realistic and, frankly, more common approach is the root sum squared method. The logic here is simple. What are the chances that every single one of your errors is at its maximum value, all at the same time, and all pushing in the same direction? Pretty darn low, right? So this method accounts for that probability, giving you a much more useful and realistic picture of your likely error. Okay, let's switch gears. We've talked about the predictable errors. Now let's talk about their unpredictable cousins. Section 3, random errors. The noise. These are the little gremlins, the unpredictable fluctuations that make your measurements jump around. You know, you measure the same thing 5 times and get 5 slightly different answers. That's random error. It can come from anywhere, a tiny bit of electrical noise, a little draft of air, or even just you not reading the scale exactly the same way each time. So how do you fight something that's random? Well, it turns out there's a really simple but incredibly powerful weapon: averaging. You just take a whole bunch of measurements, the random ups and the random downs start to cancel each other out, and the more readings you average, the closer you get to the true value hiding underneath all that noise. All right, Section 4, let's talk about a really specific and nasty type of error: induced noise. This is the stuff that can completely ruin your day if you're doing sensitive measurements. So what is this stuff? Well, think of it like this. Your measurement signal is a tiny whisper, and everything else in the room with a plug is shouting. Power lines create magnetic fields. Other electronics create electric fields. You can get ground loops if you're not careful. Even switching a big motor on or off can send a massive spike through your system. It's a whole world of invisible interference that's just waiting to mess with your data. So, okay, the world is electrically noisy. How do we protect our delicate signals? Section 5, it all comes down to smart design. You have to actively shield your measurements from all that interference. Here's your 4-point checklist for clean signals. Number 1 is just location. Keep your signal wires as far away from noisy power cables as you can. Seriously, physical distance matters. 2, twist your wires. A twisted pair is amazing at rejecting noise because the interference cancels itself out. 3, use a single, clean earth ground. This prevents something called ground loops, which are a huge source of hum and noise. And finally, 4, shield your cables. That metal braid or foil acts like armor, blocking electrostatic noise. You do these 4 things and you're in great shape. Okay, we've covered a ton of ground. Let's wrap it all up. Section 6, your measurement master plan. This is the key takeaway. Okay, part 1 of the plan is for systematic errors. The strategy is simple: identify, reduce, and quantify. Find out where the error is coming from, do everything you can to make it smaller, and then calculate the uncertainty of whatever's left over. Part 2 is for random errors. Your strategy here is to average and characterize. Take a bunch of readings to average out the noise, and then use statistics to describe how much variation you can still expect. And part 3, induced noise. For this one, the strategy is all about prevention. Don't try to fix it later. Design your system correctly from the very beginning with smart layout, proper earthing, and good shielding. An ounce of prevention is worth a pound of cure here. So there you have it. That's our guide to taming measurement uncertainty. So the next time you're in the lab or in the field, take a second look. Now that you know what to look for, think about which of these hidden errors might be lurking in your own setup, because understanding them is the first step to truly mastering your measurements.